Hello everyone. Welcome all of my viewers to this brand new video. In today's tutorial, we will be dealing with a vulnerable machine, categorized as medium in terms of difficulty. The subject of our exploration is a machine named Flick1, which is a component of the Flick series. To begin with it, you'll need to download the vulnerable image from the VulnHub website. If you're not familiar with VulnHub yet, feel free to check out these videos on VulnHub playlist. After successfully obtaining the image, the next step involves setting up the server within VirtualBox, which is a fairly straightforward procedure. Prior to getting started, you need to extract the downloaded file, as it isn't in the OVA format. You can accomplish this using the WinRAR application. Upon extraction, you'll have an OVA file that can be easily imported into VirtualBox. Firstly, launch VirtualBox. Go to the File menu and select Import Appliance. Import the downloaded OVA file. Browse your computer to locate the download file. Now, click Next. Review the appliance details and settings. You can keep the default settings or make adjustments based on your needs. Click Finish to begin importing. Once the import is complete, you'll find the Flick1 vulnerable machine listed in the VirtualBox Manager. Select the virtual machine, click on Settings, and change the network adapter to host-only adapter. Make sure that both your Kali Linux machine, which is used for performing attacks, and your vulnerable machine must be connected to the same network. Once the setup is done, it's time to start the virtual machines. You'll notice that our vulnerable machine is all set, and we now have a login prompt waiting for us. Let's dive into the fun. Enumeration. Enumeration is the first process of our attack, aimed at identifying the IP address of our target machine using netdiscover. To do this, open a terminal and run netdiscover-i and then specify the network interface name, which is ETH1. From the scan result, we have obtained our target IP address, which is 192.168.95.117. Next, we perform a network scan to detect what ports are open. Scanning the network is an essential part of the enumeration process. This allows us to understand the attack surface and plan targeted attacks. For this purpose, we'll use the popular Nmap tool. Use Nmap-sc and -sv and then specify the IP address. Where -sc is used to perform a script scan using the default set of scripts, and -sv is used to enable version detection, which will detect what versions are running on what port. After conducting the network scan, we've spotted the presence of one open port. Specifically, the port 22 TCP, running an SSH service, indicating that, if we possess valid credentials, gaining access to the server will be a straightforward process. However, since we lack both username and password, our next step involves revisiting the network scan. We'll perform an extensive scan covering all open ports. Where -a determines the target's OS, identifies service versions on open ports, and runs predefined scripts for advanced scanning tasks. Upon revisiting the network scan, we've uncovered another open port, specifically port 8881. This port is hosting an unfamiliar service named Galaxy 4D. This discovery has the potential to provide us with access to the vulnerable server's network. Upon further examination of the Nmap script, it appears that this service might involve an admin server that prompts for a password. Our strategy involves attempting to access this service, and we can make use of tools like Netcat to make this connection easier. On new terminal, type NC, specify the IP and also the port. As we already guessed, it prompts us to input password to access the new world of Flick. Let's try to guess some common password, but unfortunately, they don't work. Now, let's focus on retrieving the password. After analyzing the network scan results, we discovered another unidentified piece of data. This suggests that, when we exploit port 8881, it might reveal the unrecognized service. Now, the only option left is using SSH. To proceed, our remaining option is to utilize SSH. On terminal, type SSH followed by the IP address. The system will automatically consider your Kali Linux username as user and initiate an attempt to connect to the vulnerable service. Upon a successful connection attempt, a block of hexadecimal data will be provided. This block appears to contain additional information about the server's fingerprint. We can simplify the complex hexadecimal data using a tool like CyberChef to decode and understand its content. To do this, visit CyberChef. Now, paste the hexadecimal value into the input section. Now, search for the hex on the operations section, and then drag and drop the from hex operation into the recipe section. This will automatically decode the hexadecimal value. After decoding, I realized that the result is in the form of base 64 encoding. Let's decode it. To decode it, copy the output and paste it into the input section again. Now, search for the base 64 operation in CyberChef, and drag the from base 64 operation into the recipe section. This will decode the base 64 encoded data. However, upon analyzing the output, I noticed that the decoded data is still in base 64 format. It appears that the creator of this vulnerable machine might have purposely confused us by repeatedly encoding the text. Let's copy the output and paste it in the input section again, repeating the process until we find the correct text. After attempting multiple times, I believe I've finally identified the accurate data on my 17th attempt. You can generate a Python code to do the same thing. In a new terminal, create a new Python file named base64decoder.py using Nano Text Editor. Copy and paste the provided lines of code on my blog into this base64decoder.py file. This code is like a set of instructions for your computer. This Python program is designed to uncover hidden content from base 64 encoded text. It does this by repeatedly decoding the text. Here, paste your encoded data. Now, save your changes by pressing Ctrl+X and confirming. To make the program work, type Python 3 and mention the program name in the terminal and hit enter. The program will start decoding the text step by step, like opening nested envelopes. After a number of iterations, the program will reveal the original hidden message on 17th position. Copy the hidden message and paste it on the admin server which we previously tried to access using Netcat. Upon attempting, we find out that the password is accepted, and the door is now open. The concept of a door here is similar to a new accessible pathway or entry point. We should perform another network scan to observe any changes. After scanning the network again, we have identified a fresh accessible port. The port 80 TCP is active, indicating an HTTP service is operational. This suggests that a website with potential vulnerabilities is being hosted. Now, let's explore the website content on port 80. To do this, you can use a web browser of your preference and enter the target's IP address in the URL bar at the top of the browser window. Upon visiting the website, we discover a collection of cat pictures. Let's examine one of the cat images. If you pay attention to the URL structure, you'll notice the image's location after the IP address. Let's explore if we can access different paths using the URL. I'll remove the image ID from the URL segments. Oh no! Something didn't work as expected. Let's try removing the view segment instead, and we find ourselves encountering an index of image. Regrettably, we're unable to access any of the directories. After investigating the website, I discovered a login button that seems to offer access to the server. Let me click on Login to add a photo, which brought up a form requesting for a username and password. Notably, a hint was provided on the side. This implies that the username, demo, and the password assigned to the first user. Let's try it. However, my attempt to log in using these credentials was unsuccessful, resulting, the combination of username and password is incorrect. Let's try to brute force the login form using Hydra. Before that, I needed to intercept the data exchanged during a login attempt made with the username, demo, and password. I utilized Burp Suite for this purpose. Launch Burp Suite. Turn on the proxy through Foxy Proxy, and enabled interception within the Proxy tab of the Burp Suite program. This enabled me to capture and analyze the login data. To perform a brute force attack on the login form, we require specific login data, the cookie, username, and password data obtained through the interception process in Burp Suite. This information is crucial for carrying out the attack effectively. Now, open a new terminal and run Hydra-l and mention the username that is demo. Use -P and specify the word list for the task. Next, paste the URL. Now, paste the cookie and login data. At this point, it's necessary to modify the user and password input. And add a filter redirection 302. I find out an error. Let me address this problem and attempt to run again. However, these alterations haven't yielded the desired outcome. Hydra was successfully following the 302 redirects, but it wasn't keeping the session cookie. Consequently, every login attempt was falsely recognized as successful since the failure message wasn't present on the redirected page. To solve this issue, I created a Python program. This program utilizes the requests library, allowing it to send HTTP requests to web servers. The program reads through a word list line by line and constructs a post request to the URL. It supplies form data containing a username and combines demo with the current word from the list to form the password. The parameter allow redirects is set to false to prevent automatic redirection after the request. The server communication method is set to post. The program then examines the location header in the HTTP response. This header usually contains the URL to which the server is directing. If the location header isn't the same, it signifies that the login attempt was successful. The program prints the guest password and concludes the loop using the break statement. Here, we must include the path of our word list and adjust the URL of the login page. Once these adjustments are made, save them to a file named brute-force.py. After saving the program, it can be executed using the Python 3 command. Upon execution, the program systematically goes through the word list, attempting logins, until it successfully finds the correct password. We have successfully obtained the password using the Python program. Now, let's attempt to log in again. Once logged in, I noticed that each image has a download link. Upon clicking on a link, initiates the download of the image. If you closely examine the URL format for downloading, you might realize that it appears susceptible to local file inclusion. To explore this, I copied the download link and opened it in a new browser tab. I decided to test LFI by inserting an arbitrary path into the filename parameter. However, this resulted in an error, indicating that the file to download was invalid. I then attempted directory traversal. All these requests yielded the same response: oops. Looks like you requested an invalid file to download. etc/password is not valid. It became clear that the system was removing instances of the string .. from the filename parameter. Instead of attempting to navigate to higher directories, I decided to retrieve the source code for files in the current directory. For this purpose, I used Burp Suite to intercept the content and analyzed the changes that occurred during the LFI testing. Let's refresh the URL, causing it to trigger Burp Suite. Subsequently, the data should be sent to interception mode. Now, send this data to the repeater. This approach provided me with the source code for the index.php file in the webroot, confirming that the framework in use is Laravel. If you have read this article, then you will know the basic directories in Laravel Web Framework. If you have not yet read it, kindly read it before proceeding further. Given my familiarity with Laravel's directory structure from the article, I recalled that the webroot for Laravel applications is within a directory called public. All application logic exists in directories above this one. With the URL path now altered, the next step is sending the data. However, upon inspecting the response, it becomes evident that the requested data is deemed invalid. After a bit of thinking, I realized that if the system was simply replacing the ... string, I could potentially exploit this behavior. I aim to include ... in the output by crafting a string with ... This way, when the ... was replaced, it would leave ... within the string. Depending on how the replacement was implemented, this could enable directory traversal and arbitrary file inclusion. To test this, I requested this following URL. I confirmed that the content matched what I had previously retrieved when using ./index.php as the file name. This successful test verified my assumption, and I achieved the same file inclusion result. In the Laravel project, there's a vital file named composer.json situated in the same directory as the public directory. This file contains essential information regarding the project's dependencies and configurations needed for Composer to work effectively. Upon quick examination, I determined that the running version of the Laravel framework is 4.1. Focusing on the autoload section, this part guides Laravel on how to automatically load classes within your application. You don't need to manually include these classes using require statements. Under the class map, you'll find classes related to various components of the application. When you use any of these classes in your code, Laravel's autoloader will include the necessary files without you having to explicitly state require statements. As we're aware, the app directory is the heart of the Laravel application. It contains core application elements like controllers, models, and services. In Laravel, the routes.php file serves to define your application's URL routes and link them to specific controller methods. This organization aids in structuring the application's functions and logic neatly, facilitating easier management and development. It's important to note that in Laravel 5, route definitions are shifted to the routes directory. Let's try to attempt to access the controllers, which reside in the app directory under controller. Alter the URL path to lead to sessioncontroller.php located within the controllers directory. The standout detail is the fake SQL injection error. However, due to a type-safe comparison against false, it appears challenging to exploit. We're aiming to retrieve the contents of the upload controller initially. Interestingly, there seems to be no restriction on the type of file uploaded. Our test revolves around trying to upload a PHP reverse shell directly, bypassing the image/download route. Start by clicking on Upload a photo. Our goal here is to upload a PHP file that contains a reverse shell. So, open a new terminal to perform these steps. First, locate the reverse shell PHP file. Once located, copy it to your home directory. Let me modify the PHP file to include my listening IP address. If you're unsure about your listening IP address, you can use the ifconfig command to confirm it. Next, we have to set up a listener on our machine to listen on port 1234. Now, let me upload the modified PHP file through the website's upload functionality. Upon uploading, the website will automatically redirect you to the download page. After uploading the PHP file, you can directly access it by browsing its path within the images directory on the website. I notice an unfamiliar file on the second page. Be aware that I can't directly open it. So my only option is to download it. Proceed to download the file. Upon inspection, I realize that the downloaded file appears to be a JPEG image, but it doesn't display any image content. However, this file is likely the one I uploaded, as the website automatically saved it in JPEG format. To confirm its true format, you can open a terminal from here. Now, run the file command followed by the file's name. This reveals that the file is in ASCII text format and identified as a PHP script. It means I can use a text editor like Nano to open and explore its content. The process surprisingly turns out to be relatively straightforward. Let's check out the logic in the view controller. After analyzing the logic in the view controller, we confirmed the replacement of the // string in the target file name. Unfortunately, the file is read using file get contents instead of being included. This means we can't exploit it to execute arbitrary PHP code. For a more comprehensive perspective, we delve into the home controller component. Nothing noteworthy is found in these sections. Lastly, I explore the database configuration file. The config files define settings and options for different aspects of the web application. Please note that these details can vary based on the version. In Laravel 5, configuration files are stored in a separate directory, while in Laravel 4.1, the configuration file is within the app directory. Let's visit it. Examining the database configuration file reveals credentials, including an old SQLite database definition. Given the obsolescence of SQLite 2 and below on modern systems, downloading it is futile. Instead, I attempt to acquire the database credentials online. Let me extract the username and password from Burp Suite, directly from the response side. Let's attempt to copy the entire output into my text editor. Unfortunately, we are not able to copy it. Efforts to copy a shorter portion of the data have also met with limited success. Although we can't directly copy the complete text, we do have the option to copy them individually, one at a time. After copying each credential, I gather 3 sets of credentials. Now that we have the username and password, we can use them to access the server through the SSH service. Foothold. Now that we have 3 sets of usernames and passwords, let's try to attempt to log into the server one by one. Open a terminal and use the SSH command with the first username associated with the server's IP address. Then, provide the password. Unfortunately, the first username-password combination didn't grant us access. Moving on to the second one. But this one also didn't work. Let's proceed with the third set. Success! We've gained access to the server using the third set of credentials. Now, let's try to locate the user flag. Upon checking the files and directories, I noticed that there isn't a flag file present. However, there is a message file that seems to contain our flag. Let's view its contents using the cat command. This message seems to be like a hint, where there is a .docker file, which is present in the same directory. This .docker file seems to provide access permissions to the directories owned by the user Robin. The message even includes an example of a directory path. Taking this hint into consideration, let's attempt to access the mentioned file. Successfully, we've been able to view the content within the file. Now, let's try listing the files and directories within the user Robin using the ls command. Unfortunately, we lack the necessary permissions to access the files directly. Our only option is to use the .docker file. It appears that the user Robin might possess elevated privileges. Our next step is to discover a method to escalate our privileges and switch to the user Robin. Exploitation. As we lack the necessary password for user Robin, an alternative route is through obtaining the SSH keys. Within the SSH directory, there are two most important files are present. They are authorized keys and ID/RSA. Let's find a way to take a look at the contents. To inspect their contents, we will establish symbolic links to these files owned by the user Robin. This is accomplished using the ln command. Let's start by linking the authorized keys file to a new file named as Docker file, where -s is used for symbolic links. You can verify this using the ls-al command. Let me read the file content using the /read docker command. However, it's possible that the authorized key might not be effective. Let's also examine the contents of ID/RSA using the same approach. However, before proceeding, it's essential to remove the previously connected file. Here, instead of authorized key, replace it with ID/RSA and execute the command. You can verify this using the ls-al command. This file contains the private key necessary for accessing the user Robin. To proceed, we will copy these contents into the ID/RSA file in the same directory and then restrict its permissions using chmod +600. With the setup complete, we can use the SSH command to log in as the user Robin. Confirm by typing yes to proceed. By doing so, we've successfully gained access to the Robin user account. Our next objective is to acquire root access in order to fulfill the CTF challenge. Privilege escalation. During the process of privilege escalation, the primary goal is to gather information about the system and pinpoint any potential vulnerabilities or misconfigurations that might grant us higher privileges, ultimately leading to accessing the root level. To start, let's perform a user permissions enumeration to analyze the user's rights and privileges on the system. This can be achieved by executing commands like sudo-l or uname-it to determine which commands the current user can run with elevated privileges. Let me run the uname-it command to identify various details about the machine, such as its kernel version, hostname, architecture, processor, and operating system. Additionally, I'll examine the privileges associated with the current user by running sudo-l. After executing this command, I've discovered that the user Robin possesses specific permissions for the reset.sh file within the opt/start Apache directory. Unfortunately, this doesn't seem to be a helpful route for obtaining a root shell. Given the presence of Docker on the target machine, I'll use the docker ps command to list the currently active containers. This will provide an overview of the containers that are currently operational. However, it appears that there are no other active containers at the moment. To gain further insight, I'll inspect the available Docker images that reside within the container repository. Notably, there are several Ubuntu images accessible within Docker. Leveraging this discovery, I'll exploit the opportunity to attain a root shell. When we run this command, a fresh Docker container will be established using the Ubuntu image. The container will start an interactive bash shell session, allowing us to work within the container as if you were working in a regular Linux terminal. The root directory on the host system will be accessible within the container, allowing you to manipulate files and perform tasks within that directory. Following these steps, I've successfully gained root access. I'll confirm this by using the whoami command to verify the current user as root. Next, I'll navigate to the root directory using the cd command and confirm the presence of the root flag with the ls command. To view the content of the root flag, the cat command can be employed. To view the content of the root flag, the cat command can be employed. With these actions, the CTF challenge has been successfully completed. If you have any questions or uncertainties, feel free to leave a comment in the designated section.